Sure, Edwin. Can you hear me?
Yes, we do.
Okay, then I'll start. Uh, okay. Can you guys see my screen?
Yes, we do.
Okay, I'll start. So, hi everyone. Welcome. So, my name is Akash, and I am AI software solution engineer at Intel. Today, I'm going to present to you about uh, deep learning and like what we are doing to optimize deep learning frameworks in Intel. Like you guys must have heard of TensorFlow, PyTorch, and many other frameworks like which you are working on to create your application, AI ML application. And what we are doing in Intel to optimize these frameworks so that you don't have to change a single bit of your code, and you can just use our uh, like the same framework to optimize your workload to make it faster on Intel architectures. So let's go ahead. So in today's talk, like I'm going to quickly cover one API, the stack, software stack that we offer. Uh, my colleague Saverin and Roy and others may have talked about this, and I will just quickly recap you of this. And then I will go on telling you about data precisions, like what are the different data types, like int 8, vfloat 16, float 16, float 32, these kind of data set. Normally PyTorch or TensorFlow or other frameworks uses to store their neuron values or weight values in the memory. So I'm going to talk like briefly touch a bit about like what are the different types of data types that these frameworks uses to store the values. Then I will go about telling you about 1DNN. Like 1DNN is a backend library which Intel offers to optimize frameworks like TensorFlow and PyTorch. So I'm going to talk about these things after that. And please feel free to interrupt me if you have any doubt. Please unmute yourself and ask in the middle of the presentation, or you can ask in the chat box. But that chat box will not be accessible to me, so I will suggest you to unmute yourself and ask any question which you have. So here I'm showing you the one API stack of Intel. So here, so what is the whole pipeline? Like you have an application and then you uses some framework to develop your applications. And how Intel is optimizing your application is actually through the backend. So in the backend, our uh, many optimized libraries like which uses Intel architecture, low-level programming language, which uses actually different types of operator fusion or graph optimizations and many other different kind of optimizations it does in the backend, and it actually make it compatible with the Intel architecture. So your applications becomes very faster on CPU, GPU, FPGA, or any other hardware which you have. Uh, so this is I'm showing you like how one API in the backend is doing all the work. So this is just an overview, which you also already are familiar with. Saverin and Roy already talked about this. So in Intel, we offer multiple toolkits like Intel One API based toolkit, domain specific toolkits. Like if you are running some HPC applications, so there is a toolkit for you. And if you are running IoT kind of toolkit, which actually gives you the specific like operations for that. So every package will be pre-installed in this. So you just have to download this one API according to your domain. So if you are working on AI, ML, or toolkit, so all the tools which are important like TensorFlow, PyTorch will be already installed in this, and you can use it, and you can optimize your application and make it faster. And there is an Intel distribution of OpenVINO, which is an inferencing solution that Intel offers. And this tool, Vladimir in the next talk will cover this in detail. So what is Intel AI Analytics Toolkit? So I'm going to talk about this AI Analytics Toolkit now. Like we already offer you one package which you can download this, and all the tools which I'm showing you here will be automatically installed, and you can just directly use it. So in deep learning, we offer you Intel optimizations for TensorFlow. So if you are using TensorFlow framework, so that will be optimized with Intel low-level libraries, system-level libraries. And then we also offer for PyTorch, and we also offer Intel Neural Compressor, which Nikolai is going to talk about in detail, which is giving you the multiple features on top of your applications. Like if you want to do quantizations or knowledge distillation and many other things, you can use Intel Neural Compressor. And we also have Model Zoo, which is like a repository for optimized architectures. So if you are working with ResNet or any other transformer-based architecture, in any deep learning architecture or ML architecture, there is a optimized version of that architecture you can find in Model Zoo. And similarly, in machine learning, we offer multiple uh, uh, tools like XGBoost or Modin or Scikit-learn, Dal4Py, like these kind of tools already Roy has talked about in detail. So you can use these tools with Intel AI Analytics Toolkit. So basically, it provides you the solution if you are data scientist or AI researcher or anyone who is is working in AI ML, then they can use automatically. Like it's not a hard work to install this, and you can directly use it, and your application can become very faster. And one more thing, you can easily get this toolkit using the Intel installer or Docker or some package which you like apt or yum, or you can install it using Conda, or you can, if you don't want to install in your hardware, you can use Intel DApp Cloud, which is a cloud with a cloud which Intel offers, where you can test applications, your applications, and this Intel AI Analytics toolkit is already installed in this DApp Cloud. So you can just log in there and then just put your application and then get the numbers like performance benchmark and see how your application is performing with our optimizations. Now let's talk about the CPU. Like in Intel, currently we offer multiple. In now I'm only going to talk about in Xeon based architectures. In Xeon we offer Cascade Lake, which is a second generation architecture of Intel, which uses VNNI instruction set to make your application faster. So it can do like quantizations like int8, and so that you can uh, make it smaller, your application make itself smaller with int8 optimizations, quantizations, and you can use this VNNI instruction set with Cascade Lake. And in Copper Lake, you can also use bfloat16 kind of data type, and which is more not more faster, like it's smaller, but it can also give you the more accuracy than int8 quantizations. And then we also have this Ice Lake, which is a third generation architecture. It also uses VNNI and also uses this Intel SGX with software guard extension that can make your federated learning applications faster. And now we are going to also release in 2000, maybe next year, Sapphire Rapid, which is like fourth generation Xeon architecture. It uses AMX instruction. It is not using VNI, but it is actually making your application suffer faster with Intel advanced metric extensions. And it can also support different types of data types like bfloat16 and any other data type. Let's talk about data types. I actually was talking more like about int8, bfloat16, float16, and these kind of things. Let's talk more about this. Like, what is that? So basically, data precision or data type actually is something where your AI ML applications is actually converting your values into multiple bits like binary fashion, and is storing that in the memory. So there are multiple data types which your framework can use. So normally PyTorch framework uses float 32, and similarly TensorFlow with TF32, like TensorFlow has its own data type. So I'm going to list down here like different types of data type in deep learning. Normally, a framework uses to store the values of neurons or weights. So, int8 is one of the famous data type which you can use to store the values. And int8 means it uses 8 bits, 8 binary bits to store your value in the memory. And there is another BF16. It means brain float 16. It's another kind of data type which uses 16 bits, and there is a floating point 16 which also uses 16 bits. But in the making of these bits, there are different number of exponent and mantissa in both of them. So I'm going to talk about in detail in next slides. But this is another famous data type which you can use. And there is in TensorFlow, they use a TensorFlow 32, which uses 19 bits in total to store their neurons or weight values. And this is the most famous for floating point 32, which uses 32 bits, like some bits for sine, some bits for exponent, and some bit for exponent for mantissa. So in summary, actually, the data type, according to your data type, you can choose like how much memory you need, or how you can lower your memory bandwidth. So your application, if using a floating point 32, you can change it to int8. So from 32 bits to 8 bit, it is a tremendous amount of saving in the memory. And it also use lower storage, and it also can give you the higher performance. So it actually speed up your application because your application becomes smaller, and then it becomes faster in execution. So in total, we need to consider like when you are converting to a smaller data type, it should not lose your accuracy of your model or of your application. So in Intel, we always have this consideration and choose accordingly, like how your data type should be converted internally in the backend, so that you don't have the accuracy loss, but you also get the high performance, lower storage, and lower memory bandwidth. So in floating point 32, you can see like this is the binary representation of floating point 32. Like we have a sign bit, and then at 8 bits are used for storing the exponent bits, and then 23 bits are used for as a mantissa. And so this is a standard, very famous data type which normally frameworks uses to store the values. We have another data type like we have 16, which is brain float 16. It uses one sign weight, 8 exponent bit, and 7 bits for mantissa. And there is another FP16, which is floating point 16. It uses one sign bit, 5 bits, and 10 mantissa, 5 bits for exponent and 10 bits for mantissa. So this is pfloat 16 is an efficient replacement of FP32 in training and inference both. Like you can use this bfloat 16 type, which can make your application super faster. It can give you the 2x performance, and can also don't encounter any accuracy loss. So you can try this with Intel architectures, these kind of floating, these kind of data types. With int8, there is another data type called int8. It uses one sign bit, and other are used as a mantissa. It can give you the significant speed up, but it actually we don't know like how much accuracy it can also lose. But it can significantly speed up your inference. So if you cannot use it for training, because in training it can significantly reduce your accuracy, but in inference you can use it with a small loss of accuracy. So it is not suitable for training. And then Intel hardware means any Intel hardware uses like int8 or bfloat 16 precisions to make your application smaller and faster and more uh, uh, means you can use it these kind of data types for making your application very fast. Now I'm going to talk about the deep learning frameworks, which are very common in today's world. Like everyone is using like TensorFlow and PyTorch normally to develop their AI ML applications, and how in Intel we are optimizing these frameworks. So we have Intel optimized TensorFlow. We also have Intel optimized PyTorch. In the backend, both these frameworks are optimized using 1DNN library, which is a low-level library which Intel uses in the backend to make your application faster and more accurate sometimes. So Intel optimized deep learning frameworks are drop-in replacement. In this, you don't have to change any of your code. You can just use this framework with your application, which you have developed in these frameworks, and you don't have to change a single line of code. You just have to install this Intel optimized TensorFlow or PyTorch, and then everything will be taken care by the backend library 1DNN. And all the optimizations for TensorFlow, like nowadays, like new releases are coming up every day. So all the optimizations are upstreamed automatically in this TensorFlow or PyTorch framework. So you can uh, always will be updated with the new optimizations. So if you're using TensorFlow and so if you're using these versions of TensorFlow, so you need to consider this. So if you are using TensorFlow 2.5 in between to 2.9, you have to use Intel. There is some external flag which I'm going to talk. Okay, and there is no. You have to set Intel optimizations manually. But if you are using from 2.9 to the latest version of TensorFlow, all the optimizations of Intel will be turned on by default. So in that case, you are already automatically covered. But in this, you have to actually use external flag, or you can just use one flag uh, to actually switch on the optimizations of Intel. And before that, there is no optimization. So better is to actually install or directly from TensorFlow website, or you can directly install Intel One API toolkit and get all the optimizations. So better install latest version of everything. So you can get this optimized framework using pip or conda wheel, like you just pip install torch vision. This is for PyTorch, and you can also use it for TensorFlow installation, or you can use Intel AI Analytics Toolkit, which actually combines multiple frameworks, or like PyTorch or TensorFlow, or other tools like machine learning tools also combines. It gives you the whole package. So now there is one thing which is different in PyTorch than in TensorFlow. In PyTorch, some of the optimizations of 1DNN is not actually going like are not actually going to the upper level. So in that we offer you Intel extension for PyTorch, which actually bypass all the blocking or all the means they take some time. So this actually PyTorch is owned by Meta company. So they normally takes time. The new optimizations are not going to the PyTorch sometimes, but using this Intel extension for PyTorch, this is another package. You can bypass all that delay, and you can directly get all the optimizations which you get in TensorFlow. So this is one thing which you need to take care of. So basically same type of optimizations, but at two different levels in 1DN and in Intel extension for PyTorch. Basically all the optimizations which are not going to the PyTorch, you can get it through Intel extension for PyTorch. This is another package. So so these are the optimizations which 1DNN have, like operator optimizations, memory layout optimization, graph optimizations. So using these kind of optimizations, your application can become adaptable to the Intel architecture and become very fast. to in execution. So I'm going to talk about all of that in the next slides. So basically, we have all the Intel optimized TensorFlow, Intel optimized PyTorch, and we also give you an add-on functionality, which is in the form of Intel extension for PyTorch. So So let's talk about 1DNN, which is actually doing all the work in the backend of all the framework that you have, PyTorch and TensorFlow, and how it is optimizing your applications in the Intel architecture. So let's go deep in this. So what is 1DNN? It's an open source cross-platform performance library for deep learning applications. You can get like a high performance, like in deep learning frameworks which you have. It can give you a high performance if you are using Intel optimized frameworks because it is using 1DNN library. It uses the instruction set according to the Intel architecture. I was talking about VNNI instruction set and AMX instruction set for Sapphire Rapid CPU. It uses those instruction set and can make your application can optimize your applications. And this is open source. It supports multiple data precisions like float 32, B float 16 for training phase. In inference, it supports float 32, B float 16, float 16, and intent. So using these kind of data precisions, it can optimize your application. So you can use, and this 1DNN, it runs for both like CPU or GPU. So you can use Intel CPU and GPU and get all the optimization of 1DNN. So I'm going to talk about one by one, like how 1DNN actually do all the optimization. So first is it is a operator optimization. So what it is basically mean that it is replacing the default kernels of your framework like TensorFlow and PyTorch. In TensorFlow, they uses eigen kernels, and in PyTorch they uses Aten and these kind of operators. But with the Intel One API, you can uh, or Intel optimized framework, it actually replaces those kernel by Intel 1DNN kernels, which so all those kernels are doing mathematical operations. So now with 1DNN, 1DNN uses the Intel instruction set to make those operation very fast in Intel hardware. So it basically replacing those kernels with the high optimized kernels of Intel. Next is memory layout optimization. So basically, it is setting optimal layout for each kernels, and basically it is by minimizing memory changes in between kernels. So I'm going to talk in more detail in the next slide where I'll be showing you how in memory layout it is like doing this, like replacing the setting the optimal layout for each kernel. And in graph optimizations, in 1DNN, do operator fusion or layout propagations, which is like fusing multiple operators at once. So you don't have to uh, execute all the steps. It is actually basically using the fusion of multiple operators. So and all those operations can be executed very fast in a single step. So I'm showing you the operator optimizations, how it is done. So normally in TensorFlow, all the computation, like all the operations are using this computational graph. It converts all your operation in computational graph. And then this is a simple operation of the multiplication, matrix multiplication, add and ReLU. And how this operator optimizations. So, so this is just a example of how just giving you the brief background of how the TensorFlow is actually having multiple operations like mathmal, add, and ReLU. And now I'm going to talk about the operator optimizations. Like in this, it actually, like I said before, it replaces the default kernels by highly optimized kernels, and it is using different instruction set like AVX and VNNI, and also in Sapphire Rapid, it will also support AMX. It supports both training and inference data types. And here actually the idea behind showing you those operation was uh, in DNN you have convolution operation, you have like different kind of operation you do, pooling, normalization, data manipulations. And with operator optimization, it actually replaces all these operations with Intel 1DNN. Like it substitute those PyTorch or TensorFlow operation with 1DNN operation, so that your application can become very adaptable to the Intel architecture. In memory layout optimization, what happens is in PyTorch, normally your data is stored in this fashion. You have a batch size, you have a channel, you have a height and width for computer vision applications. So normally this format, memory format of storing your neurons or any weights value are not efficient for Intel hardware. And we with with this optimization, what 1DNA is doing is it is replacing this like you can change in your framework of storing this type of memory layout to this type. Here this is a batch, height, width, and channel. So channel at the end, and this can make your Intel like your application faster, because it uh, it is easy for Intel to do processing on your operation if your data type are stored in this fashion in batch, height, width, and channel. So this is one thing that 1DNN also do. So other optimization was graph optimization. So in this normally what happens is like you have this operation which I also showed previously in the previous slide. But in this, what you do is like if you're using 1DN and in the back end, you convert this with 1DN and replace this with 1DN and format. So you do this conversion many times, like every time you do this conversion. But with efficient layout propagation means if you are running your application in the background, you don't need to do this conversion here. You only do need to convert application when you are actually interacting with the user. So at the end, it do the conversion. It doesn't do any conversion in between. So this is an efficient layout propagation. So this is one example where 1DNN actually uh, understand this and do it for you automatically. So in Fusion computations, normally your most of the time, like about 40%, if you are using ResNet 50 architecture, 40% of your time actually is going is in bandwidth limited operations. So in this bandwidth limited operations such as RALU or like these kind of operations, your applications is wasting too much amount of time. But with Fusion, you can combine these operations. So you have a one convolution operation. Now you can combine convolution, sum, and ReLU together, and then you only have two operation here. You had here one, two, three, four operations. So you can use this Fusion of 1DN and to make your application smaller and faster. So this is another example of graph optimization, like where you have multiple operation, but you can combine those operation with fusion strategies of 1DN and can make it faster. So I talked about the Intel optimized TensorFlow, Intel optimized PyTorch, and also Intel extension for PyTorch, which are basically using the in backend 1DN to do all the optimizations. So let's talk about like what is Intel extension for PyTorch. So it is basically is providing you what is missing in the latest version of PyTorch. Like I said, all the optimizations are already upstream to your PyTorch framework. But if some optimizations are not getting passed because of delay of its company, then you can bypass it using Intel extension for PyTorch. So it's just providing user with up-to-date Intel hardware features. So all the latest optimization you can get it using Intel optimizations extension for PyTorch. And it also supports like both CPU and GPU architectures of Intel. So in this Intel extension for PyTorch, it is also called IPEX. So I will be referring this Intel extension for PyTorch as IPEX in the later slides now. You can use this in imperative mode, which is also called eager mode, and you can also use it in a graph mode, which I'm going to talk about in later slides. So in imperative mode, what happens is you can just use this like 3 line of code or 4 line of code and just add this Intel extension for PyTorch as IPEX, and then you replace this model to your torch.channel last. Like I said, in memory layout, it can make your application faster, and you just do this ipex.optimize model, and you also do it for data, like just change the memory format to use the channel last, and then just 4 line of your code, and then your application can become faster. And similarly for different data type, like this is a standard floating point 32 in this PyTorch application. All these operations by default uses floating point 32. But if you want to use a low precision B float, brain float 16 data type, you can just also use this in ipex.optimize B float 16. Just pass this variable in this ipex.optimize function. Another mode which I was telling is graph mode, which is also called torch script mode. Here you can actually use this to make your application more faster than imperative mode. In it is easy to actually optimize graph rather than imperative, like your application. So if your application is in graph mode, it can become 1DNN can actually make your application super faster because of multiple other optimizations. So you can, what you need to do is with this, you just use this as an imperative mode. But here, when you are actually inferencing, you just need to use this JIT.trace and JIT.fridge, just 2 line of addition, and you can use it in torch script mode. And similarly for vfloat 16, everything was same, but just that in the inferencing, you are just using torch.jit.trace and .freeze. So I'm going to talk about in the demo, like how it can be done. This is some performance figures which I'm showing you, like a speed up compared to the PyTorch, stock PyTorch, and this is with the latest version of PyTorch and with IPEX. So you don't see any like much speed up. So this dark blue actually is showing the IPEX performance, and this light blue is showing the stock PyTorch or the PyTorch latest PyTorch performance. You don't see much speed up in this because all the optimization, like I said, are already upstream to the PyTorch package or PyTorch framework. But some you can get some for some application like ResNet, you can get like higher speed up for 1.8 or 1.5 or these kind of things you can have. So a small speed up you can get, like it adds actually the optimizations which are missing in PyTorch. It actually is giving you this functionality, this Intel extension for PyTorch. And you can directly get it using the One API toolkit, or you can directly install this using pipwheel or conda wheel. It also you can install it using conda wheel also. So I talked about the optimization. So there are multiple optimizations which are 1DNN is doing. So I'm going to talk about in more detail about these operator optimizations, memory optimizations, graph optimization, optimal optimizer, mixed precision. So this is what IPEX is doing. Like IPEX supports all these kind of optimizations. So let's talk about graph optimizations. So like I said, graph optimizations, your application fuses multiple operators like linear operations and linear plus JLU, add plus. So there are multiple combinations you can use with different fusion strategies. And Hugging Face actually reports that 70% of their NLP task. So this is a transformer based repo, which actually is made for NLP operations. And then they are saying that 70% of most popular NLP tasks, these can get performance benefits as with such fusion patterns. So with fusion strategies, there are 70% of their tasks can get performance benefits. So this is one thing which I was saying. So in memory optimizations, like I said, like your data is normally stored in this fashion, batch, channel, height, and width. So it is actually converting your operation to this batch, height, width, and channel. So channel at the last can make use of optimizations in Intel hardware more than this, because in using this only you have to do more reorder kind of operations, uh, so that also takes some time. So with this it is a uh, with this format you can actually get more benefits of Intel hardware. So here I'm showing you with just separating this two kind of data type, memory layout operation, like batch, channel, height and width, and batch, height, width, and channel. You see here there is you have to do reordering of your input and weights to a different format. Like this is a blocked memory format, and for 1DNN to do a convolution operation. But if you are having this memory layout, you can directly use it. You don't have to do a reorder here, and you're in this, like you are benefiting with this format, and so that your 1DNN convolution can happen and your applications can become faster. Next is mixed precision. Here, uh, what happens is, like I said, like with bfloat 16, you can change in IPACS, you can change a different data type and just use this IPACS as a variable in this function. You can just pass this parameter in this function, and then you can use this bfloat 16 data type uh, for for your applications. There are three types of automix precision. You for some operation like convolution and linear, you can convert it to vfloat 16. For other operation like group normalizations or ReLU, you can convert it to a blue float 32. This is not supporting as of now for vfloat 16, so you can just directly use vfloat 32 float 32 only. But for linear operation, you can also get it converted to bfloat 16. So with automix precision, it checks like what operation you are doing, like these kind of operation you are doing, and it automatically converts according to the hardware. Like your hardware supports bfloat 16, so it converts that in that. If it is not supporting, then it just leave that as it is. So next, I'm going to show you the small demo with the Intel extension for PyTorch. Here you can see how different types of features which PyTorch Intel extension for PyTorch offers. So I hope you are able to see this demo. This is a Jupyter notebook. If it is not visible, please let me know. So here in this IPEX structure, I said like it is divided into two mode. So eager mode and graph mode. This is also called imperative mode. In graph mode, you can have more optimizations, but in eager mode, you can also have optimizations. Here, I'm just giving you a brief structure of how this IPEX structures look like. Normally, it is using this changing, like with if you are using IPEX, it is normally attend operations, actually a PyTorch operation, but with the TensorFlow, this is a eigen operations for doing mathematical things. So with this IPEX, you can use different kernel 1DNN kernels to make this operations faster. And similarly in graphs, you can use fusion operations and efficiently than in eager mode, so your application can become faster. So this is like ISA dynamic dispatch, like it uses multiple instruction set of Intel. Uh, Accordingly, it overrides the native attend operations, and it replaces it with the 1DNN kernels, so that your application becomes faster. Now I'm showing you how you can integrate your IPACs into this. I'm just giving you a example here. I will show you for training and inference both, like how you can use IPACs in training and inference. I'm now here showing you an example of how you can do a training on CFAR dataset for classification, you can use this. I'm just going to execute all the cells. So here I'm using the train dataset using CFAR and train loader I'm making using PyTorch library. Now I will also use the channel last, which I already described you how you can convert it the channel to the last format so that your 1DNN can use this and you don't have to reorder that so that your speed becomes faster. So here I will use the ResNet 50 architecture, and you can change this to memory format to the channel last. And now I'm going to execute this. And here I'm using the criteria and optimizer for your model to train. So this is a ResNet based architecture, which is giving you a different layers. Now I will integrate IPEX. Here, you just have to use 2 lines of code, import Intel extension for PyTorch as IPEX, and then you can pass the model in that and your optimizer in the training so that it can optimize your model and optimizer both. This is a training loop. Here, you can also change your data format to the channel last format. And this is just a training loop here, which you can see like how your training is happening. I'm putting a break here because I don't want to like waste too much time in training. So it will just go one loop and then it will break. So here it is executing and your application is running with IPEX in the background, and it is successfully generated. So you can train it for multiple epochs, but now I'm not showing you here. And similarly, you can do inference. So this is I'm showing for imperative mode. Here you can execute again. You can use the ResNet 50 architecture, and I'm here taking the random data variable using one batch size, 3 channel, and height and width of 2 to 4 image size, random image size. So I'm now passing this format to a channel last format, and now you can integrate the IPEX, like I said, Intel extension for IPEX, IPEX.optimize, and then you can just get the model, get the output from the model. And similarly, you can do it for bfloat 16. So I'm just going very fast here, the same steps again for bfloat 16, and with the so here, just one line here, data type, I chose torch.bfloat16 to make it run on bfloat16 type. So if your hardware is supporting bfloat16, it will use it. If it is not supporting, it will not use it. Now you can also use the auto mixed precision. So auto mixed precision is actually automatically picking the functions which are supported for bfloat16 or for other data type. So it can automatically choose it for you. So you just have to use .cpu automatic auto mixed precision .autocast, and you can just get the inference from your model directly here. So this is how it is done. And now with the IPEX in TorchScript mode, you can, this is a graph mode, like I said, I described in the presentation. The same step with the optimization, just that in TorchScript, you have to use this torch.jit for your model, and then you have to freeze it. This freeze operation is what is happening is like it is unfolding, folding the batch normalizations layer. So it is very important to do this operation in TorchScript mode, and I'm going to execute this and it will run. Some results I'm here showing like the speed up with PyTorch 1.10.1 and with the Intel extension for 1.10.100. Here you can see like the speed up of different architectures. So I will wrap up my presentation now. If you have any questions, please feel free to ask. Can you guys hear me? If you have any doubt, please unmute yourself and you can ask me.